Alright, so welcome back. We're going to talk again. Last time we talked about real numbers, we're going to go into proving that the real numbers are uncountably infinite. So, for the sake of contradiction, we'll assume that the set of all numbers between 0 and 1 is countably infinite. We're just assuming that. And that below we have written such a list right here. This assumption is true if and only if our set of real numbers has one-to-one correspondence with another countably infinite set, such as natural numbers. This also means we're assuming there's some kind of pattern that allows us to write down such a list in the form of a coherent set. In our numbers, the letters, like A1, A2, A3, represent the digits. Now, to have one-to-one correspondence, the first number in our hypothetical pattern is this right here. Second number, 0.B1, B2, B3, where each of these, B1 is just some number, and so on, down here. Also, that all decimals will be infinitely long. They're just numbers that end, like 0.3 would be in the list of real numbers. Instead, it would be written as 0.299999999. Yeah, just to make sure they're all infinitely long. Now, in such situation, every possible real number between 0 and 1 would be matched up with a corresponding natural number, and vice versa. Now, is this possible? To be clear, we're assuming every natural number has been matched up with a number in the set of real numbers between 0 and 1. But lo and behold, we can still create another real number. So to do so, let's let there be some decimal number x between 0 and 1, such that it's the number in its 10th place, this a1 right here, is not equal to a1, or this number is not equal to a1, and this number is not equal to b2, and this number, x3, is not equal to c3, and so on, and keep going down. This number would be different than every number in the set we've already had. But in order to have one-to-one correspondence, every number in the natural numbers has been matched up with all of these numbers. But we still created another number even though these are always filled. In fact, we can create an uncountably infinite amount of more numbers that don't match up with these. No matter. For this one, we can add a number. We don't know the order of this, but we can add numbers in between this order, in between this A1, A2, A3, and B1, B2, B3 that don't, instead of adding it on to the end, which we could take another natural number for, but we're actually creating a number not on the end of the list, in the middle of the list, and we can do this an uncountably infinite number of times to always create another number that we won't be able to match up with the natural numbers. So since we assumed that this our real numbers was countably infinite and found a contradiction, it must follow that our initial assumption was false, and that the set of all numbers between 0 and 1 is not countable, and therefore it is uncountably infinite. This is just a way to prove that the real numbers are uncountably infinite. But the simplest way to explain it is that the real numbers include irrational numbers, like pi. Irrational numbers, by definition, are numbers that aren't allowed to end. They will never end. Therefore, we can never count to them. You can't count to something that never ends. Unlike any rational number, we can pick, no matter what number we pick, we can't pick pi on the rational numbers. We have to pick a number that is represented by an integer fraction. And no matter what we pick, we can always count to it. The size of the set of all real numbers is what George Cantor, spelled Georgcantor, who is the founder of infinite set theory, he called this the cardinality of the continuum, the size of all real numbers. And with this idea of the continuum in mind, we have the first concept we'll need to understand, the Banach-Tarski paradox. So now let's move on. And don't worry, this section will be much shorter than the last one. It's just a quick fact about subsets with respect to infinity. A proper subset is defined as a set with all of its elements contained inside another set whilst being different from the latter set. Typically, one takes a set of numbers and removes some, and then creates a proper subset of the original set. This method can be applied to both finite and infinite sets. So here, 2, 4 is a proper subset of 2, 4, 5, as it was made by removing 5 from the bigger set. And just here, the natural numbers are a proper subset of the whole numbers. But for finites, like our first example, these two sets have different cardinalities, but these ones have the same cardinalities. Actually, something else fun we can do, we can even write the whole numbers as the sum of the sets 0 and 1, 2, 3. Then we can create the whole numbers from this, since these are the natural numbers. We can create the whole numbers again by subtracting 1 from each of these. And we've created a whole set, and we've created the set of all whole numbers from a proper subset of itself, which is just this is something that will come up again in a bit. And this type of logic is why George Cantor had to be clear when defining what an infinite set was. He said an infinite set is a set which can be put in one-to-one correspondence with a proper subset of itself. This concept is kind of neat, and it's not that difficult to grasp. It's more something to keep in the back of our heads while we delve into similar concepts. All right, now we'll get into Ian Stewart's Hyperwebster Dictionary. This is the last thing we have to cover before we actually get into the Banach-Tarski paradox. And this is also where things start to get fun. So as an exercise, a fun exercise, let's write a book that contains every possible string of letters that could be written using the English alphabet, where every entry consists of a different combination of letters. Would this be countably or uncountably infinite? Well, I haven't actually given you enough information to be able to tell, so let's answer that later. First, let's write it. This book is what's called the Hyperwebster Dictionary, and Dr. Ian Stewart theorized the process one would go about in trying to make it. First, we write down the sequence A, A, and so on, and keep going forever. After we're done doing that, forever, we would write down AB, ABA, ABAA, and then ABB, then ABBAA, and yada yada yada. And eventually we'd get to AC, keep this pattern going, and eventually we'd get to AZ. And eventually we would have every possible string of letters that starts with the letter A. But something that will be important later is here we're defining a word as any finite string of letters. Keep in mind that there's still an infinite amount of words. It's just that for a word to be a word, it has to end. This is just like the rational numbers, where we could keep adding more digits to a decimal, and it would still be representable by fraction. A number that doesn't have a pattern and never ends just is not defined as a rational number, and a string of letters that never ends is not defined as a word. Anyways. Now, the problem is, our book is going to be way too big. So we need to take as many shortcuts as we can, to help write it and keep our hand from cramping. Let's take a look at all of the letters that start with A, right here. We don't actually have to type the letter A at the beginning of every word. This could save us a lot of space, an infinite amount of letters, actually. We could just turn all the words that start with A into their own volume with the letter A printed on front. We could remove the A from every entry and just leave it to the reader to add the A themselves. They can figure it out. They could figure that out. And we can do this for all of the letters. Except now we kind of notice something. When we took out the first A, what we had left looks a little familiar. This right here. It looks kind of like what the rest of our book was supposed to look like. And actually, it's exactly what the rest of our book is supposed to look like. By removing the first letter of each volume of our Hyperwebster, we've made 26 copies of the entire Hyperwebster. Just like how we separated the natural numbers from the whole numbers. Let's see. right here, where we separated from natural numbers and changed this up to make the whole numbers again. I mean, we still had this extra copy of 0. And we got the whole numbers again. We've made, just from this, we've made another copy of the entire Hyperwebster just from volume A. And if we do this to all the volumes, we've created 26 copies of the entire Hyperwebster dictionary. Now, is it countably or uncountably infinite? You've probably guessed that it's countably infinite based on how we compared the definition of a word to a rational number. As shown here, here's one way to line up all of our words with one-to-one correspondence with the natural numbers. It's just one way to do it. You've probably also guessed that if we allowed an infinite string of random letters to count as a word, if we changed the definition of a word, then our Hyperwebster dictionary would be uncountably infinite. You might think that it isn't so, and we can still order them, because we could still order them and line them up one-to-one, but we wouldn't, not everything would have one-to-one correspondence. We would be defining an infinite string of letters as a word. For example, say we matched up, wrote down all of pi, an unending string of numbers and digits. And we matched out the first 10 letters of the alphabet like this with the 10 possible numerals, and then made the number pi, then number for letter. We then made the number, and then for number for letter, we wrote out the word with our little matching these letters up. Then we would have, in a dictionary terms, an irrational word. We would never be able to count to this word, no matter what we tried. So that would make this uncountably infinite if we changed the definition of a word. Anyways, this out of the way, we can finally move on to the Banach-Tarski paradox. Now, here we go. We are going to clone this sphere. This pictured here is a hollow spherical shell. Using this paradox, we are going to duplicate this object. This spherical shell is composed of an uncountably infinite number of points. It's like picture like the number line, but from 0 to 1, but three-dimensional and a sphere. And we're going to include all of these uncountably infinite amount of points when we take the sphere apart and put it back together. We should be aware that we're not going to be ordering them like we did the set of all rational numbers, as we can't make some pattern that will refer to an uncountably infinite number of points. But we can come up with a way to break such a set into separate pieces. Just like how if we let the Hyperwebster dictionary be uncountably infinite, we could still separate it into 26 different volumes. So, let's take some point on the surface of the sphere. Actually, I can see it here. Called O. We don't have to know where it is exactly, just know that it's here. It's somewhere on the sphere. What we really need to clarify are two unique transformations, A and B. We'll define transformation A as rotating the sphere about the x-axis, kind of this way, by 45 degrees counterclockwise, right here. And the transformation B, it will be rotating about the y-axis by 70 degrees clockwise. Both of these are from the perspective of the positive end of the respective axes. But and now we're also going to name two more transformations: A that's underlined and B that's underlined, which will be just the same thing as the first two transformations, but in the opposite directions. Like A, if our transformation A will lead us to here if we rotate it from point O to here, and transformation A with a line under it is just the opposite direction. Now, recording's about to go out again. I'll get back to you in the next video explaining how we're going to use this labeling method to make our sphere count as a little geometric Hyperwebster.